Okay, so we're going to start with our triangle, and we'll walk through the analysis a little bit. Obviously, you need to find the centroid of the bolt pattern, do your bolt forces calculation per the PDF I loaded to the assignment. You got to put your load on here. When you're picking for your restrictions or for your constraints for the nodes here, when you're set on vertices, you can change your shape to be a circle. And then when you click and drag, you can get just the nodes at the edge of the circle is one way to do it. The other way to do it is you can select surfaces, come up to the edge, pick the surface, well maybe we can. Oh, because I'm still on, I gotta change my shape. Go back to point. Okay, so now I can pick, you'll see it highlighted the whole circle. If you right click out in the open space and go down to select related and then click vertices, it'll pick all the vertices. So a couple of ways of picking the vertices for a circle when you have lots of nodes defining the edge of your circle. Then these are just set to be fixed. And then process your results. And you'll get something that looks like this maybe, hopefully. But now we're trying to determine what are the forces in the bolts. So we're going to look at the reactions in the Y and the Z. So we can set that. But as you recall, there are a bunch of nodes here, so we can't just pick a regular value. Let's see, I want my shape to be a circle. Just the circle, and then I'm going to do inquiry of results, and this will be, let's see, I had myself set to Y, okay, so here's all the current Y values for each one of those nodes, which really doesn't do us much good at this point. So if you go here to summary and select sum, then it'll sum all the Y values for all the nodes on that, to give you the reaction in the Y-axis. So now you've got to do that for 5 poles and 2 directions. So the way that I discovered to help facilitate that is if you save this to a report, and you can name it whatever you want. Just give it a name so you can tell the difference between your holes and maybe what direction you're going. The direction isn't super critical, I guess, as long as you do A or B or something to differentiate. So this was all the Y-axes, and then I can just change it to Z. It'll give me the Z number, save to report again, and that will be the numbers for hole 1. Now obviously you have to repeat that for all the other holes. Then you can go to report. And if your file names don't show up here, if you hit refresh, then it'll bring your files in. So now you can click on, so here's the summation for the Y direction of hole 1, summation of the Y or Z direction for hole 1. Then if we bag those, we get the total reaction that's there, right? And then compare that to your calculated number, and it'll be really, really wrong.
Oh, you need to calculate ahead?
Yes.
No.
So this definitely needs refining as far as the mesh goes to try to get the numbers a little closer, and potentially, maybe need to review my calculations. But yeah, my numbers are fairly disparate. So, well, actually, a couple of the holes came out sort of close, and some of them are just off by a lot. So anyway, see what you can do and we'll go from there. But anyway, so that gets you the reactions at the bolts for doing the triangle. Now, let's see, 5, 5. So let's go through 5, 5. Okay, so we have this, whatever it is, our pistol here. And let's see, you can, if you completely constrain the bottom and make it fixed, I don't think that that's completely appropriate, because this is part of a larger device and we're just looking at a portion of it. So it does affect the deflection. It doesn't affect the stress really, but it does affect the amount of deflection, which I think may be a potentially more appropriate way to constrain this is to prevent it from translating in the Z, because it's attached to another body, so it's not going to translate in that direction. And then select one node to prevent translation in the Y, so that we don't have, or so that we are restricting our rigid body motion. We're not allowing the whole thing to skate off to the left or the right. So anyway, so that's the constraints on doing those. Now, this.
So we do all the ones in the bottom in C, and one on the right in Y?
I think I did this one here as I did it in the Z and the Y.
Okay.
And then the rest of them are all in Z.
Okay.
This is the way I did. And then my mesh size for this one was 0.25. What's my mesh on this one? I want to switch to a 0.5, so it's bigger. So we'll go back to this one. In any case, oh, on the other one. Okay, so now, where's my results? Okay, so we'll do this. So once you process it, right, and we're trying to determine the stress concentration factor for these two fillets, right? So how are we going to go about doing that? What's our process, or what's our equation that we're going to use to do that? Oh, I had done a what do you call it? One of these sliding planes. And now I can't figure out how to get rid. Oh wait, let's see. Wait, let's see if I just delete all. There we go. Got it back. You did. Okay. Now we're trying to figure out what our stress concentration is going to be for this, right? Let's see. Right? So what's the definition of a stress concentration? Well, the geometry, or any kind of change in geometry, is going to be a stress concentration. But mathematically, how do we determine what the value of a stress concentration? Anybody remember? Huh?
Go to EFT.
Go to EFT. Well,
Yeah, it's E fatigue or whatever. that
E
comes.
fatigue, yeah, certainly that. But I'm thinking why it's not working. Maybe it's coming up. Okay, so what how are we calculating the stress in this piston? What's our base equation? MC over I, right? So when we okay,
You set up the K value.
you watch your toe there. Okay, so we're doing MC over I, and I've changed this to, 1/2 or 1/12 base height cubed. So it becomes this, right? The first part of our, or I don't know if it's the first part, but this part here at the end is 1 inch tall, right? And we're going to travel from the end back to the radius 4.5 inches, because that's where we have a consistent diameter. After that, our diameter, or a consistent cross-sectional area. After that, our cross-sectional area starts to change. So we're going to stop at the 4.5, right? So if we calculate our stress at the 12 is the 1/12 base.
Oh.
Okay. So we get a value of 27,000 psi at 4.5 inches from the end. So the way that we calculate our stress concentration, right, is our sigma max over our sigma average. So sigma max is going to come from our model, and sigma average from our flexure, so that's our 27. So I have a couple calculations here for a couple different mesh sizes. And I look, E-fatigue does not have this shape on it. So these numbers are from the solution manual from Peterson's, which is a big book of stress concentrations. I have now ordered my own copy so that I can look these up. But in any case, we can do the numbers and continue to refine the mesh until we get to, close to the reported value. And I didn't do a lot of refining on this one. I refined a different one. Well, we'll get to that. Anyway, so that's how you go about doing that. And the way that you find what's my stress there is you're just going to pick max. Well, so the max isn't in the right place. So the way that you pick the max then is, let's see, I'm on nodes, okay? So you're just going to come in here and pick a group of nodes. And then you're going to say inquiry. Oh, I should switch over to the other side. Hang on. So if the max probe isn't in the right location, simply make sure you're selecting nodes, make a window around the high stress area, inquiry for results, and scroll through the results and find the largest value. So 32,996 looks, nope, there's a 34,487. Okay. So you'll use this number, 34,487 divided by 2,700 or 27,000, and that'll give you a K. And then you can just continue to refine the mesh. You do the same thing when you're looking here at this other radius, right? Except for your initial calculation, you're going to do, where'd my piece of paper go? I lost it. I don't know, I misplaced my note. Okay, anyway. You're gonna have to make an assumption about your cross-sectional area, right? And what's going on there. And then you'll still, just look for the highest node there. And I will post what the solution manual says, because we can't, E-fatigue doesn't have it, and I didn't find it anywhere else. I don't know what I did with my piece of paper. Anyway, okay, so moving on. Let's go to 5.6. So similar scenario as far as, well, okay, so there's several things going on here. Right, let's go to this one. Actually, let's see. So let's see, if I go to YY tensor and select max, then it'll give me the max value, and I can divide it by what I calculate the stress is in that area, right? Because it's going to be P over A, and A is just going to be the area on either side of the hole, right? So and then you just continue to refine your mesh, and this one is on E-fatigue, so that's easy enough to look up. But if you consider the different ways to constrain this, right now, I mean, you're just pulling on it on each side, right? So if you have no constraints other than the forces that you put on it, because it's just pulling in the X direction, right, then that's what it's going to do. It'll end up cockeyed a little bit. So you have to constrain it in the Z somehow. So how would you constrain it in the Z? Well, you can maybe constrain the bottom, right? But if you do that, then you're not getting the deflection that you would normally get on the bottom for that part next to the hole. So if we constrain the ends, just at each end, but allow this to move, I don't know the numbers, but I still felt like it was affecting things or the way it was going on. So the way I ended up constraining it is, if you constrain one node on the neutral axis, then you're going to affect the movement the least, because you're on the neutral axis. So, and there's your results. And I felt like it provided better results than constraining it anywhere else. And this one actually does a great job of converging if I get all of this a little bigger. So E-fatigue says 2.16, and by going to a mesh size of 0.06, it converges within 0.4%. So it does well. Then the last thing, if we go to symmetry, because we're wanting to prove that symmetry works, and I don't know where my paper went. So for this one, the max value here for deflection was within 10% of the same masher size that we had for the full model at this particular juncture. I need to finish refining the mesh to see how it compares to the other ones, but I am confident that it will work out fine. I did try to mesh this with a frictional or frictionless constraint, right? The idea of the frictionless constraint is that it constrains it in the normal to the surface, but allows it to translate in the other directions. But when I looked at the results, it didn't appear to behave as I would have expected, so I went back to constraining it maybe in a more conventional manner. So you can see here, these constraints along the top prevent it from translating in the z-axis, and these constraints on the right end just prevent it from translating in the y-axis. And then it seemed to behave more appropriate, more the way I expected it to behave. So I don't know what I'm doing wrong with the frictionless, something we have to learn or figure out about the software, but so there's what we've got for working on these problems for now. I hope that helps.
These are doing what to these?